Guys, we are in the last section of the notes for chapter 12, which have been all about these kind of beautiful, wonderful fractals that we've been kind of discussing. This one, though, probably takes the cake. This is probably one of the most interesting, one of the most kind of beautiful kind of things that we could look at in terms of fractal geometry, and it's what's called the Mandelbrot set. Now, we're not going to get into too much of the technical details of this set. We obviously saw some of the math that is behind it when we were looking at the activity at the start of class. But in order to create the Mandelbrot set, it becomes very necessary to use a computer and calculator of some sort in order to make it much more feasible. But we are going to take a look at exactly what it looks like. So, first of all, it was discovered by Benoit Mandelbrot, who is a mathematician at Yale University. So if you're wondering where it got its name, it is the name of the person who discovered it. And again, the math behind it goes pretty well past what we were going to talk about, not only in the book but in this class. And so we're going to look at kind of the overall idea, look at some of the details of the set, but we're not going to get too bogged down in the more intricate things. So to start off, we're just going to take a brief kind of visual tour. This is what the Mandelbrot set looks like. Let me zoom in on it a little bit for us so you can see it's this kind of shape, this kind of figure. It's got kind of a heart shape to the right, and then has these other kind of smaller shapes which are coming off of it. And so let's see what happens as we zoom in. Now, to kind of discuss some of it, we'll do it kind of in the context, let's kind of think of it as a flea. So we'll kind of think about this image as being a flea. So you've got the body, which again is that kind of heart-shaped piece, which we call the cardioid. So that is this kind of piece right in here. And then in addition to that cardioid, which again is this kind of piece right here, you have the head as well, which is kind of this part right in here. And then you've got this kind of antenna-like thing coming out of it as well. And so there's kind of what it looks like, at least at first. And so again, kind of thinking of it as a flea, then what you might also notice is that this flea has some more smaller fleas kind of spread around it. In fact, if we were to zoom in on one of these sides and zoom way far in, here's what the edges of that Mandelbrot set looks like. So you can see that it has some form of infinite and approximate self-similarity, not necessarily exact self-similarity, because every time we get a little bit further magnified, it's going to be kind of the same theme, but it's never going to exactly be identical. And so you can kind of see that here where they look similar to each other, but are not the exact same. So that's the approximate self-similarity that we're talking about. Now, as we continue to zoom in, so here is another image zoomed in even further, we can see that there's even more of these kind of fleas, if you will, that are kind of preying on the larger image. And we can see that there's a lot of variation. Notice that kind of around the edges we have these kind of interesting pictures and images which surround the fleas themselves. You can almost think of them as being part of maybe like the coral reef, at least as far as what the textbook kind of refers to it as, where you've got these urchins, some seahorse tails, and especially the seahorse tails that we'll see in the next couple of slides become a little bit more obvious and kind of interesting. So let's zoom in even further. And as we do so, notice that now we've got even more stuff that we could talk about. We've got these shapes that are almost like starfish or anemone and different things. Very interesting. And again, keep in mind, this is just, it's an image that's been zoomed in way far from that exterior of that main Mandelbrot set that we started with. So you've got this happening infinite number of times around this image that you could keep zooming in and look over here on the right. You could continue to zoom in on any of these different pieces around the edges and get a whole new picture, a brand new kind of image to look at. In fact, as we continue to zoom in, you'll start to notice more of those kind of seahorse tails that we were talking about before, where you've got these kind of vibrant images, you've got these different things coming out of them, very kind of exotic, kind of fun to look at. And here's where things get kind of crazy. Here's kind of the magnification of one of the slides from the previous slide. So now we've zoomed in even further. So remember, we started with this massive Mandelbrot set that we've continued to zoom in on and zoom in on and zoom in on. And eventually, you'll get to a point where as you continue to zoom in, you will continue to get closer and closer and closer to that original Mandelbrot set that we saw in the very first image. So after all of that zooming in, after all of these images, and you continue to zoom in, you eventually get to a point where the process starts all over again. And so then as you continue to zoom, we now have a new Mandelbrot set, which we could continue to zoom in on. And we could continue to do that theoretically an infinite number of times. And you'd continue to see these features and these developments, and really kind of a cool thing to kind of look at. So again, keep in mind that this is zoomed way far in. It's not as if we've just added some extra colors and images to the exterior of it. But this is a zoomed in image of the original Mandelbrot set itself. Very kind of interesting and kind of hard to wrap your mind and brain around in a way to try to understand it. So obviously anywhere we would choose to look at these pictures, if we continue to magnify enough, we would continue to get those copies of the original Mandelbrot set. That would always be surrounded by another changing, always stunning background, and you could continue to do this all the way around that original set. And so you've got the infinite and approximate self-similarities, which blend in with the infinite repetition, infinite variety, creates this kind of landscape that's exotic, that's diverse. It's almost as if it's a part of nature itself. Now, the building blocks of the Mandelbrot set are complex numbers. And in fact, if you remember in the activity from the start of class, we talked a little bit about these complex numbers. And it's built by using what's called a recursive process. So again, that idea of a recursive process where we're doing the same step over and over again, like we've seen with the other fractals in this unit, continues to be the case in this part as well. Now, keep in mind complex numbers can take on a variety of forms, the basic building block of which is the complex number I, which is equal to the square root of -1. So when we use I, we can build all sorts of other numbers. We can have full complex numbers like 3 plus 2i, negative 0.125 plus 0.75i. But also what's interesting is that you can also get all of the real numbers. Like if you wanted to get the number 1, that would be the complex number 1 plus 0i. So not only do complex numbers involve some of these other types of numbers, but they actually encompass all of the real numbers as well. In fact, there are more complex numbers than there are real numbers, which is odd to think about because you would think that there were an infinite number of real numbers, and there are. And so it's weird to kind of think about that there's actually more complex numbers than the infinite number of real numbers. And so kind of an interesting thing to think about. Now, something we also mentioned in the activity was that there's a plane that we can use to graph complex numbers. So we talked about the complex numbers, a plus bi, can be converted into these points like a comma b. And so basically what that means is that we can study these geometric interpretations of complex numbers through the course of operations that we do on them, and especially the Mandelbrot sequence. So the Mandelbrot sequence is right here. Obviously we saw this a little bit in the activity as well. But you start with your seed, which you pick whatever number you want that to be, call it S. It can be a whole number like the number 2. It could be a complex number like 1 plus I. It could be anything as long as it's a complex number. And then what you're going to do is you're going to take the square of that. So you're going to take your seed squared plus whatever your seed number is, and that gives you S1. You then continue that process. So the next would be to take S1 squared plus your original seed, that gives you S2. And then you take S2 squared plus your original seed, that gives you S3. And then you take S3 squared plus your original seed, that gives you S4. So you can see that this process continues to repeat itself until infinity, essentially. So again, it's a simple replacement rule that we just talked about. Here are the definitions of those in case you wanted to copy them down. But again, it's a pretty simple process. Should be a pretty easy rule to remember. Now, Every single point in the Cartesian plane is also a complex number, and thus it's also the seed of some Mandelbrot set. Now, the pattern of growth is going to be determined and is going to determine whether the seed that we started with is either inside the Mandelbrot set, in which case we are going to label it as a black point, or outside, and that's going to be some non-black point. Now, the color we're going to decide based on whether it's escaping and exactly how fast it is escaping. So if you remember in the activity, we did this example where our seed was just the number 1, and as we continued at step 2 and 3 and 4, we got larger and larger numbers, and by about the 7th or 8th time, we got to numbers that were so large that it almost was hard for the calculator to be able to handle those numbers. And so in that case, we call the set an escaping set. And so when a set is escaping, we assign it a color. And that color is dependent on exactly how fast it's escaping. So the basic rule is that escaping sets are not part of the Mandelbrot set. So escaping sequences do not count, so they're not going to be black. Instead, here's kind of the rule that we use. It's not really a specific rule. It doesn't tell you exactly what color is going to be assigned. It's more based on kind of a spectrum or a range of colors. The hot colors like reds and yellows and oranges are for seeds that escape kind of slowly, whereas the cool colors, which are the blues, the purples, and so on, are for ones that escape very quickly, which in a way you might think of as kind of reverse or kind of inverted from what you would maybe want to think. But those hot colors are ones that escape slowly, meaning that they grow very slowly, whereas the cool colors like blues and purples are ones that escape quickly. And so again, if we wanted to continue doing this, we could continue doing it by hand or even with a computer and calculator to help us out, and we would just label each of the points based on how fast it was escaping. So again, for our seed of s equals 1, it was escaping, if you remember. It was escaping pretty quickly, and so we would probably use a cool color like blue in order to label that point. The next type that we saw, if you remember, was what was called a periodic Mandelbrot sequence. And so when it was periodic, it was alternating between a couple of numbers. And when we have a alternating sequence or a periodic sequence, we're going to say that it is part of the Mandelbrot set, and so it would be assigned the color black. So remember, if it's inside the Mandelbrot set, we assign it black. If it is escaping and it is outside, we assign it a color based on how fast. And so in this case, we would color in s equals -1, our seed of -1, as the color black. All right, the next one we saw right here, -0.75. Obviously, we saw this in the activity. Wasn't quite clear at first, but the more we did it, the more we saw that it was alternating and really kind of fixed around a certain value. In fact, the longer you do it, the closer you get to -0.5, and we called that an attracted sequence. In other words, the sequence was attracted to that particular value. So we will also sometimes call that an attached sequence. And so again, when that happens, whatever the value is that we are getting closer to, we call that the attractor. So the attractor for our seed of -0.75 would be the number -0.5. We could also say that the sequence is attracted to -0.5. Either way would be an acceptable way to kind of put that. Just like we said with periodic sequences, when you have a Mandelbrot sequence that is attracted, then we color in that seed as black, and it is a part of the Mandelbrot set. Now we can also have periodic Mandelbrot sequences, and again we saw this in the activity, so we were able to see that when we started with a seed like s equals I, that eventually you get to a point where it just becomes periodic. Obviously at step 1 you get -1 plus I, at step 2 you get -I, and then it just starts to repeat itself over and over again. When that's the case in a periodic sequence, we are going to say that that point is a part of the Mandelbrot set, so it would be labeled as a black point. Now, it's also possible to have multiple attractors. In fact, if you were to look at this sequence, which again, we did not get a chance to look at this one in the activity, but kind of interesting nonetheless, you can see that At certain points, you're getting closer to values. For example, S0, S3, and S6 are all very close to each other. S1 and S4 are very close to each other. And S2 and S5 are very close to each other. So you actually have 3 different numbers that are being cycled around in here. And so this would also be an attracted Mandelbrot set. Again, because it's attracted, we would go ahead and label that point as black. Okay, so here is kind of the key slide. This is the one to make sure that you have written down and that you study over before the quiz on Wednesday, which is the definition of exactly what is the Mandelbrot set. Well, we say that if the Mandelbrot sequence is either periodic or attracted, then the seed is going to be a part of the Mandelbrot set and is going to be assigned the color black. If the Mandelbrot set is escaping, rather, then the seed is going to be a point outside of the Mandelbrot set, and then we're going to assign it a color that depends on the speed at which the sequences are escaping. Again, hot colors for slowly escaping sequences, and cooler colors for the quickly escaping sequences. Now, we've left out some of the technical details, but these are kind of the main ideas behind those amazing pictures that we saw at the start of these slides. Provides a lot of aesthetic for not a whole lot of mathematical investment. Again, if you think about using your calculator, it becomes pretty easy to let it kind of run itself. In fact, it's become one of the most popular mathematical things of our time that we've kind of had a chance to study, and that is it for the Mandelbrot set. All right, guys, that is it for Chapter 12. At this point, you should be ready to finish up any of the homework that you could possibly want to work through, and then we will take our quiz the next class period. Until then, have a great rest of your day.